Hello everyone, and welcome to today's SAC walkthrough. Hope you've all had or are having a pretty great day today. So today we'll be walking through the Unit 1 Area of Study 3, and we have a mock sample prepared here to walk through this topic of electricity. Sometimes this topic can be a somewhat confusing topic, but today we'll be doing our best to walk through and explain how to go through each of these questions as proficiently and efficiently as possible. So here we have our cover page. It's a pretty standard cover page. So you get in our mock SAC 10 minutes of reading time and 60 minutes of writing time. Of course, I'd recommend you go and try and attend the SAC beforehand using the download link available, and then come back and refer to this video afterwards for the correct solutions. So approved materials is going to be fairly as standard. You'll get one scientific calculator, a laptop to be brought in, of course. So many of you might be familiar with, say, the TI-30XB here, which could be otherwise known as that green calculator. And you'll also be allowed a page of pre-written notes. This usually should be pretty standard as for each high school, but some schools can vary. You'll, of course, also be able to get the formula sheet and the actual SAC itself, of course. So without further ado, let's get started with the SAC. First, we get started with section A, which will be 8 multiple choice questions to start. So, question 1. A talking plush toy needs new batteries. It requires 3 AAA batteries rated at 1.5 volts each, wide in series. What would be the total output voltage when the toy is in operation? So, this one is a series circuit. Fairly straightforward question, actually, because as we all know, series versus parallel, if you have a series circuit, each component is just going to be wired right in after each other. Unlike that circuit down there, actually quite conveniently placed. So, as I'm sure most of us remember, all of us hopefully, all you have to do is just do 1.5 plus 1.5 plus 1.5, which of course is going to equal 4.5. So that means that our answer is D. No, moving on. So moving on to that parallel circuit that I just mentioned before, we'll have to use it now to answer questions 2 and 3. So we have a circuit here with a 3-volt battery. It's got 2 cells. Then we also have, wide and parallel, a 1 kilo ohm resistor and a 5.3 kilo ohm resistor. So, question 2, what is the total resistance of the simple circuit shown above? So remembering back to our total resistance parallel formula, it's always going to be 1 over your total resistance. It's going to be equal to 1 over each of your parallel branch resistances. So here we have branch 1, then branch 2. So that means that we can make this first fraction here 2 or 1. Doesn't really matter what order you do it in. And we will make this 5,300 and 1,000. Put those together on your calculator, you'll end up with what is likely going to be quite a funky number. So if we do this straight into decimals, you will end up with 0.001119. Now, that is still, however, 1 over the total resistance. So we'll actually need to do the inverse of this to get the answer, which is our total resistance. Doing the inverse of that leaves us with 841 ohms. That is our answer, B, right there. So question 3, assuming that the resistors are perfect ohmic devices, how much current is being used with this current circuit setup? Pun not intended. But the first thing we have to identify in this question is the perfect ohmic devices phrase here. This refers to pretty much, and it can pretty much interpret it as just the devices all follow Ohm's law. So that is, they all follow V equals I R. There's no change in that. So what this means is that we can pretty much just use this formula. So if you plug everything in, then we already know our total resistance, it's 841 ohms. And our voltage is 3 volts. So 3 equals I multiplied by 841. Make that nullify 1. So that means that I is going to be equal to 3 over 841, which happens to be 3.6 milliamps. Answer A. Moving on to the next question, a bit of a road learning question, actually. So select the correct statement below about thermistors. So A, their resistance increases with increasing temperature. B, their resistance decreases with decreasing temperature. Interesting. C, their resistance increases with decreasing temperature. Well, it's getting a bit different now. And D, their resistance is independent of temperature. Now, I'm sure we can all immediately cross out D because we know that the therm in thermistor refers to temperature, like a thermostat. Now, there's two ways in this question. So one way is going to be sort of just knowing what thermistors are. And that would lead us to put our answer as C. The resistance goes up as your temperature goes down. However, another way you can sort of approach this question that you can see here is how number A says that the resistance goes up with increase in temperature. So ohms goes up with temperature going up. And B says that ohms go down with temperature going down. Except these are the same. It's the same relationship. So the answer actually can't be A or B. So while it's definitely recommended that you actually understand how thermistors work, there is sometimes some ways you can get around having to actually think a bit too hard. Save yourself some time, actually. So, question 5. A physicist determines that his light bulb used 40 joules of energy in the span of 5 seconds with a current of 5 amps. What was the input voltage? So we have a bit of a problem-solving question here. Let's draw this light bulb here. So let's do it's kind of like an ohm symbol in a circle. So we have a light bulb. We have some power source here. Don't really know what else is in the circuit because they didn't really tell us. What we do know is that the current was 5 amps. The time was 5 seconds. And the energy used was 40 joules. Now, this will require us to think about what sort of formulas we have to actually use. And with these here, the formula that we can use, since we need to know what the voltage is here, we need to use just stop, I got a mistake here. All right, so moving on to question 5 here. So we have a light bulb, and this light bulb uses, let's write down our parameters right here. It uses 40 joules of electrical energy. Our time frame is 5 seconds. And our current input is 5 amps. What are we looking for? Looking for the input voltage. So with these values right here, we pretty much have to decide what sort of formula we're going to use. And in this case here, this actually turns out to be a two-step question here. So we can't just take one formula to get the answer. So we first actually want to determine the charge. Why is that? So the reason for that is going to be twofold. So there's two formulas. E equals QV. Or maybe more precisely, for our purposes, V equals E on Q. We know what E is because we know it used 40 joules, but we don't know what Q is. But how can we find Q? Q equals IT. So charge is going to be equal to current multiplied by time. We do know current multiplied by time. That is going to be 5 multiplied by 5. 25. So now we know that we have a charge of 25 coulombs that's passed through. All we need to do is just put that in to the formula. Go there. So our energy is 40 joules, charge was 25, and this ends up equaling, it's my calculator, 1.6 volts. Answer A. Now, moving on to question 6. A common saying is, it's not the voltage that kills, but the current. Using your knowledge of electrical safety, which one of the following statements in reference to the saying is most correct? Let's go through them. A, it is true, since a low current power source cannot do any bodily damage. It's a bit suspicious. B, it is true, because voltage denials does not affect survivability in an electrical accident at all. C, it is false, since a high voltage shock will always result in serious injuries. D, it is false, since both the variables of voltage and current contribute to mortality. I'd break it, but it's only D could be possible. So the reason for that is because A, low current power sources cannot do any bodily damage. If you remember from what sort of the thresholds are for damage to a body, the one probably most of you remember is that 200 milliamps is enough to result in death by cardiac arrest, or atrial fibrillation, actually. So 200 milliamps doesn't sound like a lot of amps to use. It's like less than what your phone charger uses. Except you're not going to get killed from your phone charger. And that leads me on to the next point. So B, it is true because voltage does not affect survivability in an electrical accident at all. It absolutely does. The reason why we don't get enter atrial fibrillation from a phone charger is because the resistance of our skin, it's quite high. It's in the tens of thousands of ohms, actually. And to pass a resistance like that, you need an extremely high voltage paired with this sort of current. So B is false. C is also incorrect because high voltage shock does not always result in serious injuries. A perfect example of this is going to be static electricity. So static electricity is so that when you rub your feet on the ground and then you go and grab a door handle or you shock one of your friends, the voltage for that is actually quite high. It's usually in the hundreds to the thousands of volts. The only thing that makes it pretty safe actually is because the current is almost negligible. It's in the micro to nanoamps. There's basically no current. It's just a voltage. So that way, while the voltage can technically breach the incredibly high resistance of our skin, it doesn't actually do any harm because there's no energy to be deposited. So moving on to question 7. In terms of circuit design, select the most correct statement about the difference between DC power supplies and batteries. A, they're greatly different, as DC power supplies are always more powerful than batteries. Right off the bat, I have to say that this one's completely wrong. Now, don't actually try this, but if someone went and to go and lick the terminals of a car battery, they would be in for quite a shock. So B, they have very little difference aside from the battery eventually running out of charge. That could potentially be right. We'll come back to it in a second. C, they're greatly different since DC power supplies constantly change the direction of current. That's completely wrong. DC stands for direct current. It doesn't stand for alternating current. This is what that's referring to. An AC power supply will do that. They have little difference, as both are always able to complete any circuit. Not really correct, because this one's isn't a bit of a technically question, because you could have a circuit like this. Let's say you've got a diode there. Diode's going. Oops. Let's go like that. Now, it doesn't matter what we put in there. If the polarity doesn't match the diode, then it's not going to complete the circuit. So that last statement is also incorrect, which causes us to say that B is the correct statement. Now, a bit of a nigger in this question, sort of, is how this phrase here, in terms of circuit design. Now, we could go on and on about whether it be battery chemistry or how DC power supplies work, like using like an alternator and then putting a split ring on the end of it. Then mechanically, they're quite different. But we are just talking about in terms of putting them into a circuit. So you can say even like on a page of circuit design, they're pretty much identical. So identical, in fact, that the symbols are basically the same. If you have a single cell battery and a DC power supply, there's almost no way to tell the difference unless someone explicitly marks it on the power supply. At least in VCE, there are specific symbols outside of VCE. So, question 8. How much power does a 240 volts personal computer use if it utilizes 30 coulombs of charge in 5 seconds? Let's get these variables down. So, voltage is 240. Charge is 30. Time frame is 5 seconds. So, there's a formula in one of the previous questions that we did. It was question 5 that is going to help us with this. And it's pretty much, we only need one formula from this since we're not talking about current. So here, we have this one here. Energy is equal to charge multiplied by voltage. Look, we have charge and voltage. Let's find out energy first. So we have E equals V multiplied by Q. 240 multiplied by 30, according to my trusty calculator, is 7,200 joules. That's not enough for our final answer, though. It asks for power. What is power, though? Power is simply just energy over time. It's the rate of energy change, basically. That would simply be 7,200 over 5. That leads to a final answer of 40 watts, which is C. That's a multiple choice start. So we'll start with the short answer now. Section B. Start with a pretty simple question. Label the following circuit diagram components. Now we have a resistor here, and we have a line going through it. What is this? It is a variable resistor. With a circle and a cross going through it instead. This one is a light glue. We have a disclaimer about that one, but I will elaborate on that after the next one, which is, well, for those paying attention, I probably would have spoiled this one already. It's a diode. So, on the line globe, actually, there is the other symbol that sometimes more commonly used, that you might have seen used before. It's called the ohm symbol with a circle around it. That can also be a line globe as well. Both of them are correct. It's sort of in the same sense as to how variable resistor can look like that too, but you won't really commonly see that because that's an absolute massive lines. The diode, unfortunately, always stays the same. There's nothing different about that. So, moving on to the next question. List one difference and one similarity between fuses and circuit breakers. Fairly straightforward. So, fuses. Let's talk about them first. So a fuse, if you remember correctly, is, if you visualize them, they kind of, if ever those of you have seen them in real life, they kind of just like a tube that has a very thin piece of wire in the middle. This outer section is glass, and these are your terminals. Though really, there's no positive negative. You can use them either way. They're non-polar. A circuit breaker, on the other hand, could be a whole bunch of different things. So your household circuit breakers will very commonly have some appearance that looks like this sort of. You got like a switch, and it's attached to this block, and you have these big beefy terminals on the end that will attach to your circuit breaker block. Say like off or something. When the current is breached on both of them, what happens? This one, it melts. This one switches to off position. All you got to do to reset it is pretty much just walk out the house, flip it on, and it'll be back to pretty much usable conditions. It doesn't break. That fuse, though, needs to be replaced. So one difference is going to be fuses melt and are single use. Unlike circuit breakers. There's one mark. What about a similarity? Now, we have a really wide range of things we could say, but if you want to be comprehensive, then you could just say they are both electrical devices, electrical safety devices specifically, that protect circuits from current overload. They simply stop too much current going into the circuit. There's your second part. You might have a teacher that might accept they are both electrical safety devices, but I wouldn't push my luck too much on that. On to the next question. You've got a voltage divider right here. For question 3, and this is a 2-mark question. That's pretty standard with most of these. Almost single-step questions. So, what would the input voltage be required for an output voltage of 5 volts if R1 is 10 ohms? Let's say what? Oh, and a bit of a backtrack actually. Here's those funny squiggly resistors that I was talking about before. And if R2 is 8.5, that was, we don't know that. Question mark rooms. So this one's fairly straightforward, and you probably should have had it on a cheat sheet. And we just need to know what the voltage divider equation is. So we have V out equals V in is the tricky part, unless you got it written down. It's going to be R2 over R1 plus R2. So we'll just put that all in. The voltage in. Can't actually put that in as currently. So we will have to get an output voltage of 5 with a voltage in, because we don't know. But that is 5. Don't know what the input voltage is. So we'll continue with this. 8.5 over 10.0 plus 8.5. And pretty much just solve the voltage in. This will give you the answer of 10.88 volts. Now, here's our first mention of significant figures, actually. Now, for those of you who may potentially have not looked at significant figures, it pretty much refers to the amount of decimal places, not decimal places, place values in an equation, and place values that are considered significant. So here's a quick rundown. So feel free to skip over this section, of course, if you've already done significant figures. If we had a 10.0, that would be 3 significant figures. If we had a 0, 1, 0.0, that would still be 3 significant figures. So pretty much any digit in a number is going to be significant, except for leading zeros. That's simply it. The main rule to remember is that we can't make more significant figures. You can't make something more precise than it already was previously. That simply doesn't make any sense. So if we look throughout this question here, we realize that the lowest and maximum significant figures we used was 2. 8.5 is only 2 numbers in that. So we want to reduce this number down to 2. 11 volts. That will determine basically how much we have to round up. A lot of teachers in year 11 probably aren't going to check for this, but it's a good habit to get into for year 12, especially where they definitely will be checking for significant figures. And we're going to put that in the box so we actually get the mark. Next question. Question 4. We have a simple circuit running off a 9-volt battery here. Well, here's what I was talking about. Battery symbol and DC power supply symbol are virtually indistinguishable. So anyways, we have to calculate the total resistance of this circuit. Fairly straightforward question. So we just need to break this up into 2 branches. We have branch 1 and branch 2. Branch 1, the resistance, so RT1, is simply just going to be 2 times 4.7 times 10 to the power 3. It's kiloohms. This will leave us with 9,400 ohms. Next, we have, well, we already know that RT2 is going to just be 5,300 ohms. So now what we have to do is just do the parallel circuit resistance formula. So we'll have to go 1 over RT equals 1 over 9,400 plus 1 over 5,300. We are then left with an answer of, we'll get this big number out. So you will get a ridiculously tiny number of 0.000295. That's still 1 over RT though, so we then need to do RT is equal to 1 over that again. And you will be left with quite a large number compared to this one of 3,389 ohms. Now, let's think about significant figures again. So this is only a 2-mark question, so you probably won't get marked for significant figures, but as I said before, good habit to build up. So this one's fairly straightforward. 2 significant figures, 2 significant figures, and 2 significant figures. There is no mistaking it. It uses only 2 significant figures. This is going to be approximately equal to 3.4 times 10 to the 3 ohms. You don't want to use kiloohms because the unit in the box actually is only ohms. So put that in. As for marking allocation, so in these sort of working out questions, you are pretty much looking at 1 mark for the working out and 1 mark for the answer. The key when it comes to the working out is the substitution. So if you like, if you've got way too much time on your hands, you can do an actual formula. Do 1 over R1 plus 1 over R2, and then do like an arrow, and that will show that you know substitution. However, the more quicker way to just do substitution is just to do it straight away, essentially. So if you're ever not sure or stuck on what to do in a question, put down the formula, substitute the values in. Even if you don't know what to do after that, you will get at least 1 mark in there, because that is what the VCE criteria is. What's the next question? Calculate the total power consumption of the circuit. So as we established before, power is simply energy over time. There is, however, another way to work out power, but we first actually have to work out the current. So we already know what the total resistance of this whole circuit is. It's 3,400 ohms. So we'll put this here, actually. And we want to use this one from the previous question, because we already have the value. So we can use Ohm's law to figure out the current of V on R. Our voltage was 9. And our resistance is 3.4 times 10 to the 3. This will leave you with a current of 2.6 multiplied by 10 to the negative 3 amps. Now, power consumption. So energy over time, as shown in one of the previous questions, is one way to do it. However, we of course have the Ohm's law's formulas, E equals VI. So now we know the voltage and the current. We can simply just take the voltage of 9 multiplied by 2.6 times 10 to the power of -3, end up with a wattage, 2.4 times 10 to the -2 watts. That's that. We'll put that into the answer box. There's 1 mark. And I would say substitution into one of these formulas would be another mark, because it's only a 2-mark question. Will the upper branch or the lower branch receive more current in part C? Why? 2 marks. Fairly straightforward mark distribution. You're just going to talk about one of them is going to be the statement, the other one is going to be the reason. So let's zoom out a bit and let's look at this circuit again here. Now, the number one rule when it comes to current is going to be that current always follows the path of least resistance. Which path has the least resistance? Well, path 2, of course, got less total resistance. Path 1 had a resistance of 9,400 ohms, whereas the lower one only had 5,300 ohms. So we can say the lower is 1 mark. Just put in that statement there. Current always follows path of least resistance. And easy peasy. There's another mark there. That's our question done. So let's go into question 5 now. Susie and Harry are having a heated debate about household electricity infrastructure. Susie says that household circuits are wired in series since the current does not change throughout a series circuit, whereas Harry says that they're wired in parallel for usability's sake. Using your knowledge of these 2 types of circuits, identify and explain which student is correct and why the other is incorrect. Include reference to another real-world application that greatly benefits from being wired in parallel. So this is quite a large question. We have 4 marks here. So the mark distribution is pretty much going to be 1 mark for who's correct, 2 for the explanation, another 1 for saying the application. That's it, there's 4 marks. So we're going to say who's correct. So Susie says that they're wired in series since the current does not change. Doesn't really make sense. We don't really need to have current not changing. And if you think about it in a house, when you go through each power socket, it's usually the voltage is the same. We always have 240 volts in Australia, for example, and if you're, for some reason, in America watching this video, it would be 100 volts there. So we, in this case, are going to say that Harry is correct, of course. Now, this isn't always necessary, but it's a good way to sort of like bulletproof your answer. You then want to say that Susie is incorrect. And then proceed to talk about why. Susie's incorrect. As a lack of current change is irrelevant to household circuit design. Next point. So let's think about it. So with Harry, what he's basically saying is that it's wired in that way to make it more usable, but how does it make it more usable? So in a series circuit, we essentially will see, as you probably know, the series circuit needs to be fully completed for any electricity to actually run through any of the circuit at all. So let's say, for example, you want to go heat up a Pop-Tart in the toaster, and your brother in the other room is busy playing his PS5, and your mum is just about to use the iron, but none of it is going to work because your dad hasn't plugged in his buzzsaw yet into the power port at the front door. Well, that's essentially what would happen in a series circuit. Household circuits being in parallel is pretty much what provides the ability to actually like use different points everywhere and to have each point independent of another point. You're quite a massive pain if you have to turn on everything for everything to actually work. And it's not just having everything connected, everything has to be operating for it to actually work as well. So in a series circuit, every socket, you also need to turn on all your lights as well, and get expensive pretty quickly. Socket needs to be operating for it to be completed. And we'll just put in brackets, current flow, because current won't flow if the circuit's not completed. And what's our go-to example, everyone? It is Christmas tree lights. So Christmas tree lights, pretty infamously, short, cheap ones anyways, are wide in series. And when one in the middle of the chain breaks, the whole thing breaks. It's not like, oh, one breaks and then everything else afterward breaks. No, the whole thing just stops because the series circuit isn't completed anymore. So Christmas tree lights would also method. And there's that. We got 1 mark for our correct explanation. Well, Sandra is correct. Now, 1 mark for saying one reason why Susan is incorrect, and another one for saying why she is also incorrect. And last one is for our application. So let's move on to the next question. Question 6. A simple circuit is depicted below. Identify and explain the mistake and how you would rectify it. So this one is a pretty egregious mistake if you ask me, because we've got a voltmeter here. Now, what do we remember about voltmeter and ammeter positions? Well, the voltmeter here isn't really measuring anything. So the way a voltmeter works is that it's meant to measure the sort of potential difference. So it's meant to measure the potential difference between 2 points. And for that reason, the voltmeter should actually be rectified here. Should be put in parallel to whatever you're trying to measure across. Because in this case right here, you're going to measure a potential difference of 5 volts and then 5 volts again. So there's really no point at all. Not to mention that a voltmeter usually has quite a high resistance as well. And the reason for that is to stop electricity flow from going into this branch here and instead just going straight instead. So voltmeter is in series. That's our first point. That's 1 mark. The voltmeter measures potential difference across 2 points and will not provide useful info in series. You're pretty much going to find the voltage drop of just the voltmeter itself, which isn't very useful. So it should be in parallel over the light. There are your 2 marks. So 1 mark is going to be identifying the problem, another mark is going to be explaining it, and another mark is going to be saying what you do instead. Fairly straightforward. Let's move on to question 7, a much more complicated circuit this time. So we have a far more complicated circuit here, or maybe at first glance. So this circuit here, we need to calculate the total resistance of it. And one thing to recognize here is that this whole like jumble of like wires here, it's really just meant to throw you off because the way this bottom section of the circuit actually works is simply just having a resistor there, another resistor here. Here's your battery. And then in between that, you have a diode here that is going to another resistor that goes straight. It's a positive, it's a negative. Now, the issue here is that the diode's the wrong way around here. So what essentially is going to happen here is that you're going to have conventional current coming through, and it's going to not go through that diode point there. So that means that this entire 5 kilo ohm resistor section is going to get completely nuked, and we're only going to be looking at the other resistors. Hence why a bit of a hint in this question is that it's only one mark. So we can't have any more than one set of working out, and that more than one set of working out is just going to be simply 10 kilo ohms plus 3.5 kilo ohms, which is 13.5 kilo ohms. Adjust that to significant figures, and that is going to be 1.4 times 10 to the 4 ohms. And we will put that in. That's that. Go into section B. What is the current measured at the positive terminal of the battery? Now, we haven't changed anything in this circuit yet. So the circuit is simply still just 2 resistors and a battery. So all we have to do in this case here is going to be identifying what the total current is throughout the circuit, because it's a series circuit, nothing changes. So we know that our voltage is 5 volts. Our resistance, we calculated it before, is 1.4 times 10 to the 4 ohms. And we don't know what current is. So V equals IR, Ohm's law to the rescue. We will have I equals V on R, which is 5 over 1.4 times 10 to the power 4. There's your first mark, there's a substitution. Now that is going to be equal to 3.7 times 10 to the power of negative 4 amps. And that's it. There's your second mark. 3.7 times 10 to the negative 4. Pretty simple. So the next question is a bit of a trick question because it says what is the current measured at the negative terminal of the battery? It's the same. The circuit right now is a series circuit, so nothing changes about the current. And another sort of point as well is that if you take both terminals as well, even if you had a parallel circuit, all your branches will be joining together before that terminal. So it's still going to be the same anyways. So it's the same again. 3.7 to the negative 4. So now here's probably our first big question in this paper. Would there be any change in the power consumption of the circuit if the diode was removed from the circuit? Support your answer using calculations. Now, the first thing when it comes to this is we have to redraw the circuit here. Well, we don't have to redraw the circuit, but it would be quite useful to redraw the circuit. One way you can redraw the circuit is going to be just making everything like this instead. So we'll put the resistor here. Here's the branch that had the diode in it, but there's no diode in it anymore. And then this was the other resistor right here. There's that. Let's double check our ohm values. So we have, that was 5K. This one is 10K. And this one is 3.5K. All right, so here's our new circuit diagram. Diode's been removed. And this will probably be your first mark as well, because I mean, you guys could do it without the redrawn diagram. It's a good way to pick up the 3 marks. So we need to figure out what the new resistance of this parallel section right here is going to be. So the resistance of the parallel branch Again, it's 1 over again. But if you really want to take a bit of a shortcut, I'll show you guys actually. And what you can do instead, if you want to do it all in one line, is just 1 over 5. So we'll do 5,000 for simplicity's sake. 1 over 3,500. And put that all -1. It's a power -1. That will immediately like flip it over. So when you get your final answer, that final answer happens to be calculate 2058.8 ohms. Now, if we want to find the total resistance, what we have to do is just add that to the 10K ohm resistor. That means that our total is 12,058.8 ohms. That's our total resistance. So now we just need to sort of work out the power consumption, and we'll just have to use this other handy form actually. So we have that off to the side there. We'll do U power consumption. And that is going to be P equals V squared on R. So there's that. It just saves us having to do the use the current as well and using less calculated values. So our V, our voltage, was 5 volts. Put that up here so I don't scroll again. So 5.0 squared over 12,058.8. That results in 2.1 multiplied by 10 to the power of -3 watts. So there's our new power. However, we need to also need our old power. So old power consumption. Once again, P equals V squared on R. Got 5.0 squared. And what was our original R? Well, it's 1.4 multiplied by 10 to the power of 4. Put that in, and you will get 1.9 multiplied by 10 to the power of -3 watts. Those numbers are different. So we will say, yes, there is an increase in power use. So there's that. So you get 1 mark for calculating the new power consumption, another mark for calculating the old power consumption, and 1 final mark for making the right statement. Quite an involved question, but still pretty straightforward in the end, actually. Move on to the next one. So, question 8. We have a VCE Physics student taking some self-revision extension work in the field of electricity in their dad's garage. They determined that 1,350 millicoulombs of charge passes through a wire they're holding in the span of 5 seconds. What magnitude does this equate to? So let's whip out our current equation. We'll go I equals Q on T. I'll put in our values that we already have. 1, 3, 50, and that's a milli, so we're going to do a 10 to the -3. Then put that all over 5, it's 5 seconds. That is going to equal 270 milliamps. Ooh, that seems a bit dangerous. Those who remember from about maybe half an hour or something ago when we were talking about deadly amperages. So, that's that, 1 mark question. Unfortunately, it turned out that a rat had chewed through this cable previously, leaving open an exposed section which they grabbed onto with wet hands for over 4 seconds. Using just this information and your knowledge of electrical safety, determine and explain the most likely outcome for this student. So, what did we say before about 200 milliamps? Death is very likely. So the current was over the 200 milliamps threshold, making death likely. What else there? So we have wet hands on there. So their hands were wet. So that would lower your skin's resistance. What else? They held it for more than 4 seconds. Making death even more likely. And one last point I have to say to round this all out. So their lowered skin resistance made it far easier for the current to pass through at lower voltages. So the implication here is essentially what I was going into detail about before, about how your skin has an extremely high resistance. However, that resistance doesn't really matter if it's either wet or if your voltage is stupidly high. In this case here, the hands are wet, so sucks to be them, sort of, would decrease their chance for survival, quite unfortunately, which the next question sort of spoils. So an autopsy conducted found that the student had suffered atrial fibrillation. Yikes. What does this tell us about the path of the current taken through the body? So what is atrial fibrillation? Atrial fibrillation is essentially, here's some guy here, he's got a giant heart, he's got a blob in the middle. So atrial fibrillation is essentially when your heart beats unusually. So when your heart beats not in the correct pattern, it usually means that 1, it won't pump blood correctly. 2, blood won't get to important places correctly. 3, death if left untreated. So it's essentially a heart attack, really. So the most obvious thing about the path of travel taken, so to actually get to that heart, you have to go through the heart somehow. So either going to go from the top to the bottom, bottom to the top, or the most likely case is going to be through the arms. So current went through heart, likely by each arm. Enter/exit. So if they were grabbing onto the cable like this, could have gone through here, come back around here, and then come out there. Cause a heart attack. Additionally, extensive burning was also evident. Explain why electrical burns often occur when sometimes someone comes into contact with a high current power source. So, burning. How do we have burning happen? So burning happens when there's too much heat, right? So having too much heat means that there's a lot of energy being dumped into the medium that's going through. So what this essentially means is that as current passes through a resistance, the higher that resistance is, the more likely there is to be heat generated. It's kind of the way heaters work. But we want some formulas to back it up though. So we'll first make a statement saying that when current passes through a load, heat is deposited accordingly to the resistance of the load. As per P equals I squared R. So we want to use this formula here. So P is going to be power. Pretty universal concept of high power means it's probably going to be higher heat as well. And we have current and resistance. We essentially just want to use a formula that's going to relate some sort of energy to current and resistance. And this one's pretty perfect to do it. So as per P equals IR squared, if R is high, and then we're going to put that bracket, we're going to acknowledge the situation here, like human flesh, then P, well, didn't want to get rid of that G. So then P will increase. And turn into heat. Heat causing burns. So there's that question done. Quite a grim and unfortunate end to this for VCE Physics Year. So now we're on to question 9. This is going to be sort of the token practical question. Every single one of your SACs, or maybe the whole SAC itself, is going to usually be a practical analysis. This case here, in question 9, we have below are the current measurements of a particular device taken at various different input voltages. I have an input voltage of 1 volt, 3 volt, 5 volt, and 8 volts. That corresponds to a current measured of 0.5 volts, 1.5 amps, 2.5 amps, and 4 amps. So our first task here is going to be using the information in the table provided, plot the data points, and draw a line of best fit. Let's have a think. So we want to use, there's a few rules here when it comes to actually getting more marks here. The first one is going to be to use more than 50% of the space. That we have to do to get 4 marks. You would do a tiny, little baby graph there, you're not going to get your marks. Next thing we want, labeled axes. Well, it asks for it, but we need a line of best fit, of course. And if applicable, but it's not in this case, but I'll just put it out there, error bars. Now we don't have uncertainty, don't need to worry about error bars. So in this case here, we'll make our graph. So I'm going to sort of plot a bit of a rough one, considering that I'm on my iPad. But normally, if you're in the actual classroom, you'll want to use an actual ruler to do this. So let's give us a bit of space. Take one there. Take another one. Be about the same dimension there. Move that down. Now, a bit of a disclaimer actually before I continue the rest of this graph. Please do not do your graphs in red. Do them in black. I'm going to be doing this graph in red for readability's sake, so you can actually see the graph on this paper. All right, that's that. Next thing we're going to do is label some axes. So we count our blocks here. 1, 2, 3, 4, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. This is 25 up to here. And our current measured, so we want to put our dependent variable on the y-axis because that's just typically how we usually lay out graphs. This goes up to 4, 25. We can go up to 5 actually. We'll just divide by 5. So 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. 2, 1, 2, 3, 4, 5. 3, 1, 2, 3, 4, 5. 4, We're only going to go that high, but we can also just put in 1, 2, 3, 4, 5. Oop, take that 1 down from this one. 5. And you can go outside of the graph, the squares, it's fine. Just make sure your plot points are actually in the squares. So we'll have current A. Really want to be precise, you can say current measured. It's going to be dark, actually, let's turn on the light. All right, that's better. So next, we then want to work on the voltage axis. So we will label this first, actually. So voltage, what they call it, input voltage, that here. There's that. We can put axes labels there. Input voltage, we go from 1 to 8. Let's count the number of squares we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's 25 again. We have 8. Let's do 10. 10, maybe? Reduce that down from 25. 4. Okay, we can do 8 actually, and we'll do 3 for each. So 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. That will be 1, 2, 3, 4, 5, 6, 7, and then 8. Now we can plot our points. We've got everything else on this graph ready? Yes, we do. So I'll put the points in blue so it's easy to see once we do that line best fit. So we go from 1 and then 0.5. So current measured, 0.5, 1, this point here. Then we go from 3 to 1.5. Would be about here. We go from 5 to 2.5. 5 to about here. And we go from 8 to 4. That would be right here. Now, luckily for us, this is quite a simple line of best fit. As you can see, I can actually make this line of best fit using the straight line tool. And very close. There we go. So you're not always going to have lines of best fit that are going to be this perfect and actually get into the dotted lines that easily. So usually if you have points like above, like under, like that, as long as there is equal distribution of points above and below the line, you'll be good. Get rid of those dots there. Have we got everything? Yes, we do. That would be all 3 of your marks. You got your labeled axes, line of best fit, and you got your plot of points on there as well, which we can see in blue. Let's move on to the next question. B, using the graph that you have created, determine whether the device is ohmic or non-ohmic. Thus calculates its resistance. So, when it comes to a current and voltage graph, there's one very easy way to tell if it's non-ohmic or ohmic. So this line here, as we just established before, was very easily drawn by just doing a straight line. That means that it is ohmic. It's the current and voltage increase linearly, essentially. So what we basically are saying is that it's following the Ohm's law formula. So V equals I R, right there. Now, in this case here, this one's actually a bit interesting because we can swap it around and say that I equals V on R. So this is going to get a bit mathematical here. Table shook. But this here is essentially a linear relationship. If we look at this sort of as y equals x mx, here there's no plus c. The m in this case is going to be your 1 on r, x. That 1 on r there is referring to that straight line there. And if you follow a straight line, you can fit into this relationship fairly easily. So in this case here, we'd say, yes, it is ohmic. So to prove that it's ohmic, we can calculate its resistance essentially just by finding the gradient of this line. Now, there is one catch here, though, that even some of the best students can fall for, and it's just to use the gradient line. So let's do that right now. Now this is a bit of a cheat. I will sort of take responsibility saying that I usually do this in the exam, but now when they say using your line, if you have a straight line that goes through all the points, just use the table. You got a perfectly good set of values there. You don't want to mess it up by taking some like strange points on the line. Just use what you already given. Don't do that for a curved line. That wouldn't be very good. So let's calculate the gradient. To rise over run. That will be 3.5 over 7, which is 1/2. Now, you might be tempted just to say that the resistance is half an ohm. That's not the case. Because as I just mentioned before, the gradient of this graph is 1 over r. It's not actually r. Because, so let's take a bit of wrapping your head around, but that y-axis there is your current, and the y equals mx. X is the x-axis and y is the y-axis. If we get the normal Ohm's law formula where you could just use the resistance as your gradient, as the gradient as your resistance, it looks like V equals IR. Now the issue with that is that V is clearly not the y-axis because it says current measured on the y-axis. That would be I. That means that we have to swap these around, and then we'll be left with I equals 1 on R V. And that looks a lot more like y equals mx. But that means that 1 on R is equal to that gradient we just calculated, which is half. This means that the gradient is half and the resistance is 2 ohms. That's it. So we'll put our answer in, and there we go. That is the paper finished. So hopefully we're able to go through this mock paper in a comprehensive and understanding way. And I hope you found this walkthrough today helpful. And of course, we would love it, of course, if you could check out our social media, hit that subscribe button, hit that like button, and we'll hopefully see you next time for another walkthrough of another mock SAC. Bye.